Hi, welcome all. Welcome to this class. In this class, we are going to study the first law of thermodynamics. Before starting learning the first law, let us understand what is internal energy. The internal energy of a system of particles is the sum of the kinetic energy in the reference frame in which the center of mass is at rest and the potential energy arising from the forces of the particles on each other. So you have studied a system and a surrounding, system, a boundary and a surroundings or environment. So if I have a system, that system's internal energy is nothing but the sum of the kinetic energy and the potential energy. This kinetic energy is due to the kinetic energy of the particles in the reference frame, where the center of mass is at rest, and the potential energy is due to the forces from the particles on each other. The internal energy is a state function, that is, it depends only on the values of the macro parameters and not on the method of preparation of the state. That means it depends only on the state of the system. So we can say the internal energy U is a function of volume and temperature. So U depends on the kinetic energy of the particles in a system and an average interparticle distance interaction. So the internal energy depends on the kinetic energy and the distance between the particles of the interactions. So if there is an ideal gas, there is no potential energy, therefore only kinetic energy is there. Therefore the internal energy is purely kinetic. So you can see here the internal energy of an ideal gas with F degrees of freedom. Since there is no potential energy, it's only kinetic energy. So the number of degrees of freedom into half NKT will be the total internal energy of a system. How does this internal energy of air in this room change with temperature if the external pressure is constant? So here you have F by 2 NKT. So instead of KT, we know that the N is given by PV by KT. So that will become F by 2 PV. So an increase of kinetic energy of the individual molecules with temperature is compensated by the decrease of their number. So here you are seeing work and heating. We are often interested in the change in internal energy and not the absolute internal energy. So the change in energy is due to the energy flow between a system and its environment due to the change in temperature across the boundary and a finite thermal conductivity of the boundary. So that means the system and the surrounding exchanges heat because of the change in temperature. And the work done can also cause a change in internal energy. That means any other kind of energy transfer across the boundary, like work done. So the two things which causes a change in internal energy are the work and the heating. And work and heating are both defined to describe the energy transfer across the system boundary. Okay. So what are the different types of heating process or cooling processes? One is called conduction, convection and radiation. These are the three processes where the heat is transferred from one system to another. Now we come to the first law of thermodynamics. According to the first law of thermodynamics, the change in internal energy of a system is the sum of the energy, that is the heat Q, and the work. So we can say delta U is equal to Q plus W. So one thing is the heat contained in the system plus the work done. So if the work is done on the system or by the system, there can be two things. If the work is, say for example, the sign convention says that the heat and the work is positive if energy is flowing into the system. So you see here, for a cyclic process, the initial and the final internal energies are same. There will be no change in the internal energy. So the heat change is equal to the minus of the work done. So if Q is 0, the work done is 0 for a cyclic process. So perpetual motion machines of the first type do not exist. You can see here a quasi-static process. What is a quasi-static process? It's a very slow process where any intermediate state can be considered as an equilibrium state. So what is the advantage of a quasi-static process? The state of a system that participates in a quasi-equilibrium process can be described the same number of microparameters as for a system in equilibrium. So now we will just to say that a quasi-static process is a very slow process, and we can say any state in between the two processes can be considered to be in equilibrium. For example, isochoric, isobaric, isothermal and adiabatic processes are quasi-static processes. So work done in this case is by an external force on a gas enclosed in a cylinder with a piston. The force is Pa into dx. Pa dx is minus P dV. So the work done is minus integral V1 to V2 P of P dV. So the change in energy is equal to Q minus P dV. That means the work done is P dV. That is W. So the work done is minus P dV. So the work is negative. In this case, if the volume is decreased, if the volume is decreased, that means the work is positive. If the volume is increased, the work is negative. So the work is negative. That means the gas decreases its energy by doing some work on the environment. So this is what the statement of the first law, the change in energy is Q minus P dV. So in this case, the work is negative. That means the gas decreases its internal energy. That means the volume is increased and the gas has decreased its internal energy by doing some work on the environment. So if the system does work on the environment, the work is negative. If the system gets work from the environment, the work is positive. But the internal energy is a state function, but the work and heat are not state functions. That is what the meaning of this slide says. So thus we come to the complete end of this first section. That is the first law of thermodynamics. The next section we will be dealing in the next class.